For the moment, we have to use internet for these type of seminars, and I hope it will be useful anyway. Let me try to share my. As Professor Ketikanian already mentioned, I will give this talk about substrate integrated waveguide technology. And I will try to share with you my experience in this area, having in mind that most of the activities nowadays are oriented towards new applications like 5G. And this requires some particular care in terms of size of the device, of new design techniques that are flexible and can respond well to the requirements of the applications. And also another topic that is not very much considered sometimes, that is the use of unconventional materials for the implementation of microwave devices. Before starting the technical part, I would like to thank very much the IEEE student branch of the National Institute of Technology of Tirci for inviting me, and it's really always a pleasure to give a talk for a student branch, because I think it's very important to stimulate and to help young professionals to develop their skills in the area of microwaves. My talk is organized in 5 parts, as you can see in the current slide. In the first part, I will try to give a short but hopefully complete idea of the current trends in microwave technology towards 5G. So I will show you which are the basic requirements, basic technological requirements of 5G technologies and applications. And so what we need to keep in mind when we select the proper technology to implement our microwave components, and especially microwave systems. In the second part, I will illustrate the basic concepts of a substrate integrated waveguide, SIW. Probably most of you are already familiar with SIW technology because it's becoming quite common in the last few years. But I will try to give a short overview for those of you who are not yet very familiar with it. And then in the following 3 parts, I will focus on 3 aspects that I consider extremely important. The first one is related to miniaturization. We want to have waveguide components that are as small as we need for particular applications. Traditionally, waveguides have always been considered a large and bulky device. We try to demonstrate how, by using SIW technology and particular solutions, we can miniaturize this component, scaling their size down to a dimension that can be compatible with many applications. The following part will be related to some design solutions where we fully exploit the flexibility of SIW to implement novel components. So we exploit some, let's say, solutions like playing with the dielectric material or using multi-layer configuration and so on to add additional flexibility in the design phase. The last part is devoted to materials. I will show you how SIW components can be implemented by using materials that are quite unconventional for microwave applications like 3D printing, textile, and paper. And we will see that different applications may require the use of these materials. So let's start with the current status and the current trends in microwave technology towards 5G and right now also 6G applications. So when you think about microwave technology, what comes to your mind can be the use of metallic waveguides. They've been very popular for some decades, especially for radar systems, for space applications, for all those areas where you need large power and low losses. The other concept that probably comes to your mind is related to PCB, printed circuit boards, that are low-cost solution for many commercial applications nowadays. And probably the third concept could be related to the use of dielectric resonators, absorbers, radomes, or rather the electric materials that are used for particular solutions. So this is more or less what you connect with the concept of microwave technologies. But then if you think at the current, let's say, major applications, for instance, in the area of the IoT, Internet of Things, well, many applications can come to your mind that go beyond the traditional IT and networks and can include the security systems and public safety that can range from let's say, the alarm system of your house to scanning systems in airports or train stations and many other systems that use millimeter waves nowadays. Or you can think at the monitoring of industrial processes. Especially in Europe, there is a lot of activity related to so-called Industry 4.0. That is the idea to improve the quality of industrial processes by a distributed monitoring of the production. So for this monitoring, you need sensors that are distributed in your machines, and you need wireless connection between these sensors. Another area that is developing very much under the umbrella of the Internet of Things is the big topic of healthcare and biomedical systems. There is a bigger and bigger trend, a significant push in the area of healthcare to develop some sensors that can be integrated in clothes, can be worn by people, and these range from the smartwatches that can measure your heartbeat or your movement to more sophisticated systems that can be used in the hospitals and can somehow partially replace the work of nurses and doctors, because they can monitor in a continuous way the health situation of a patient, so that they can be less invasive than the traditional monitoring, and can be more effective because they provide a continuous monitoring. Of course, also in this case, you need sensors, and you need wireless connection between sensors and central processing units. Besides that, there are the smart homes, all the gadgets that are becoming popular for the homes, to listen to music, to switch on and off lights at the proper time, or all these systems. And also in this case, of course, you need a significant amount of wireless connections. And then, of course, energy management like smart grids and all related topics. So under the umbrella of IoT, there is a really large number of potential applications, and basically they all require sensors and wireless circuitry, wireless connections. And besides IoT, there is another buzzword that has been very popular in the last years. That is 5G. And 5G is somehow the backbone for IoT, because it will provide the infrastructure for all these applications. But when you think at 5G, there are a few concepts that immediately come to your mind, and they are essentially millimeter waves. So 5G for the first time will bring mobile phones to operate at millimeter waves. So we shift all our applications up in frequency, and this allows broader operation bandwidth, higher bit rate and a lot of advantages. But on the other hand, it poses a serious and very critical requirements to the microwave circuit, to all the electronics need to work at higher frequency, but with low losses, limited power, and and possibly low cost. And the other concept that comes together with 5G is reconfigurability. We need to develop some wireless systems that, besides being at millimeter waves, low loss, low cost, should also be able to reconfigure, to change operation frequency, to change the direction of pointing of antennas, and so on. So a lot of requirements, a lot of technological requirements to meet all the needs of future applications. I like to show this graph because it gives an idea of the number of devices we are supposed to implement in the next few years. And you see that the number of wireless devices, the devices connected to the internet, is really growing fast in conjunction with 5G and IoT. And according to this plot, I mean, there are many of these graphs in the internet. You can just search and find different numbers. Someone says in 2025 we'll have 35 billion devices like this one. Someone says 60 billion, 50 billion, whatever. But the message is that the number of wireless devices is growing fast. And if we want to cope with these requirements, what we need is a technology that is low cost, easy to integrate, easy to develop. So this is the basic message for the next generation of wireless devices. So if you look again at the first slide that I have shown with metallic waveguides, standard PCB, and electric resonators, well, what we can say is that traditional microwave technologies in most cases are not suitable for the emerging applications. What we need is a new paradigm for the technological requirements of 5G and IoT for the next generation of wireless systems. And what we need is a technology that allows for low cost operation at millimeter waves, easy integration of complete systems. This is a key point. Integration is one of the most critical aspects for the future microwave and millimeter wave devices. We need to develop systems and not components. This is something. This is a change in our way of thinking. We need to think at the very beginning and at the complete integration of the system, not anymore at the separate components that can be integrated at the end, but complete wireless systems. So integration is very important. Of course, we need to keep in mind also the possibility to develop wearable devices that are becoming more and more important. And if we want to do all these in a short time at a low cost, we also need simple design rules. So somehow, if we want to reduce it to two keywords, all this discussion, what we need is a good integration technology that allows to implement complete systems, complete wireless systems. And we need to consider the use of suitable material that are tailored for each specific application. So we need to go beyond the traditional either metallic or dielectric material that are typically used for micro applications. And we will see some of these materials during this presentation. So to meet all these requirements, a possible candidate is a substrate integrated waveguide technology. And let's try to understand why. So when you think at traditional transmission lines for micro applications, the two major devices that come to your mind are the microstrip lines and the rectangular metallic waveguide. And the microstrip lines are light and compact, They are easy to fabricate with a very low cost, but they have the drawback that when you move at high frequency, let's say 30 or 60 gigahertz, losses are significant. And also undesired spurious radiation that creates crosstalk between adjacent parts of your circuit are not negligible. On the other end, we have the metallic waveguide that are non-planar structures, and they have low losses. They are completely shielded, so they have no crosstalk even between closely spaced devices. But they are bulky and quite expensive, and especially there are serious issues whenever you want to integrate active devices with a metallic waveguide. You need special transitions to a microstrip line or a coplanar waveguide, and then transition back to the metallic waveguide. So if you compare the advantages and disadvantages of the two structures, well, you can recognize that the advantages of one structure are the disadvantages of the other. So one is light and low cost, the other is bulky and expensive. One has high losses, the other has low losses. So somehow we have a technological gap between the two types of transmission lines, the planar ones, the microstrip lines, and the non-planar one, the metallic waveguide. The idea of the substrate integrated waveguide is to catch the best of the two technologies. So the idea is to implement in planar form the classical rectangular waveguide. So if you look at the drawing on the left-hand side of the slide, you see that the substrate integrated waveguide consists of the electric substrate with top and bottom metal layers and two rows of metal cylinders, of metal vias, that define the side walls of the rectangular waveguide. So if you look at this structure, it looks like a rectangular waveguide, but it is implemented by using an electric substrate, exactly like a microstrip line. If you analyze this structure a bit more in detail, you see that also the propagation of electromagnetic waves inside this structure is very similar to the one of the rectangular waveguide. So this is the analysis of the fundamental mode that propagates in this structure, and you see that looks like the T10 mode of a rectangular waveguide. So this SIW structure looks like a rectangular waveguide, behaves like a rectangular waveguide, but it is fabricated by using the technology that is typical of planar circuits like microstrip line or coplanar waveguides. And this is the big advantage. So we try to merge the advantages of a rectangular waveguide and the advantages of the planar structure like microstrip lines. In this slide, I try to report a few of the first SIW components that have been proposed by different groups, some of them in Canada at École Polytechnique of Montreal, others in China, mainly Southeast University. And you see here that there is a filter that is implemented by using two rows of metal cylinder and four metal posts that define three cavities. A very simple structure. This is a filter at 27 gigahertz. The size is probably a couple of centimeters, and the thickness is in the order of 1 millimeter. This is just electric substrate. You can implement a bit more complex structures like a diplexer. You see here there is a T-junction and two filters, one channel and the other channel. Or you can implement a circulator. You see here in the center the ferrite cylinder. Or other filters like here, a dual mode filter. Or you can implement active devices like oscillators. Here you see a feedback oscillator where there is an SIW cavity as a frequency selective element in the feedback, or reflection type oscillator, mixer, amplifiers, different components that can be implemented in SIW technology. In most cases, the idea is to translate a waveguide structure directly into a SIW technology. So for instance, in this case, this structure can be also implemented by using classical waveguide technology. Here is just translated into SIW. We will see in the rest of this presentation that we can do much more with SIW because we can fully exploit the flexibility of this technology well beyond the idea of simply translating rectangular waveguide components into planar form. This figure is an example I like very much because it reports a complete FMCW radar in SIW technology. This was proposed by the group of Professor KU around more than 10 years ago. And you see that in one single piece of substrate, there are two antennas, one for receiving and one for transmitting, a mixer, a power divider, a microstrip, rat race structure, some baseband lines or IF lines, DC bias, and so on. And of course, on top of this structure, you can mount the active devices. They are not present in this picture, but of course, here you can mount amplifiers, here you can mount the transistor for the mixer and so on. So the interesting point is that you can use one single technology to implement complete systems. So SIW technology allows to implement passive components, active components, and antennas, and to have everything integrated in one single piece of substrate. You can easily imagine which is the advantage of this solution. This is a complete radar at 24 gigahertz. Imagine to build such a radar by using, for instance, horn antennas, two horn antennas, some parts of the circuits in PCB, the filters in waveguide technology, and so on. And then you have to mount everything together. So the cost can range, can move from a few tens of dollars in this case to thousands of dollars in the case of a hybrid technology. So this is somehow the most significant advantage of SIW technology, the possibility to have complete systems implemented by using one single fabrication technology. In this slide, you see how popular SIW technology is becoming in the last years. So you see in the vertical axis the number of IEEE journal papers, and in the horizontal axis the calendar year. You see that the first papers were published around year 2000, and then the number of papers on this technology started to grow, and this year, in the first half of the year, so this is updated on July the 10th, we already have almost 200 IEEE journal papers. That means that at the end of the year, we are going to be probably here. So a lot of groups worldwide are working on SIW technology, and a lot of companies, even big companies, are investing significantly on SIW research. But let's try to see what we can do with SIW besides the traditional translation of waveguide components into SIW components. One of the major aspects that attracted academic and industrial research in the last few years is miniaturization. And the reason is quite simple. If you think at just a straight interconnect in SIW technology, you have a waveguide. And as all waveguides, you need to work in the single mode band of the waveguide. So from the cutoff frequency of the fundamental mode, T10, to the cutoff frequency of the second mode, T20. It is typically 1 octave. So the bandwidth is 1 octave. This is not much for applications. In some cases, it's okay. In some cases, it's not. But the other big issue is that if you want to set your cutoff frequency of the fundamental mode at a certain frequency, for a given substrate, for a given electric permittivity, you set the width of the waveguide. So there is no way to reduce the size and keep the cutoff frequency at a certain value. Of course, you can increase the permittivity, but up to maybe 9 or 10, but it's quite hard to get low losses if you go beyond the permittivity of 9 or 10. So to reduce the size of SIW structures and to possibly improve the bandwidth performance, a lot of solutions have been proposed in the last years. And in this slide, you see some of these examples. So one possibility to reduce the size of SIW structures is using a folded solution, like a C-shape structure. In this case, you simply fold the SIW structure around the metal septum, and you get a field distribution like the one shown in the picture. So what happens here is that you reduce the width by a factor 2 at the cost of a dual layer technology. Another interesting, this was proposed by the group of Professor Grigoropoulos in 2005. Another interesting solution is the half-mode SIW. In this case, you cut away half of the structure and you leave the remaining half. Due to the low aspect ratio, so the low thickness compared to the large width, what happens is that here there is a quite large capacitance that mimics a virtual magnetic wall. So in the remaining half of the structure, there is still the same field distribution, the same half mode. And the advantage is that in this way, you reduce the width of the SIW by a factor 2 without the need of using a dual layer technology. You still use a single layer technology and you have a reduction by a factor 2 of the width. Of course, you can have some some small leakage, but in most cases, especially for transmission lines, this is more than okay. Another solution that we proposed in 2005 with a group of Professor KU was the slab SIW. In this case, the idea is to have a dielectric substrate with 2 holes in the side portions of the waveguide. So this is a cross section. The gray is the dielectric substrate. The white parts are air holes. If you consider the fundamental mode is a T10 mode and is more concentrated in the center where there is a dielectric, whereas the second mode is more concentrated at the sides where there are the air holes, this solution allows to shift up in frequency the cutoff frequency of the second mode because it sees a lower effective permittivity. So this solution allows to increase the operation bandwidth of the structure by keeping at the same frequency the T10 mode, that same cutoff frequency, the T10 mode, and shift it up in frequency, the second mode. Another solution that we propose, again with Professor KU in 2010, is the ridge SIW. In this case, we have a ridge post, a partial height post in the central position of the broad wall. And what happens in this case is that the fundamental mode, the T10 mode, is strongly affected by the ridge that increases the capacitance per unit length and so shifts down in frequency, cutoff frequency of the fundamental mode. The second mode is practically unaffected by the presence of the ridge, so it doesn't change its position. So in this way, we shift down in frequency the cutoff frequency F1 and keep constant the cutoff frequency F2. So we increase the bandwidth and we have also a lower resonance frequency for the same width. So somehow we miniaturize the structure. This is the concept of miniaturization applied to straight interconnects. But of course, you can apply the same concept to cavities. For instance, if you have a square cavity like this, and you fold the cavity around a metal septum, you can reduce the footprint of the cavity by a factor 2. If you connect these cavities to design a filter, you have a net advantage of reducing the size of your filter by a factor 2. Actually, we can do more. And for instance, we can do like in this case where we have a folded cavity. You see the lower part here, the top part here. And we define some insets in the central metal septum, and we use these insets to control the resonant modes of the cavity. If you look at the color plot here, you see that in the absence of any insets, we have the fundamental mode of the folded cavity and the second mode of the folded cavity that looks like this. So they are quite different. They are quite largely spaced. One is 4.7 gigahertz, the other is 7.4 gigahertz in terms of resonance frequency. But when you insert the 3 insets, the first mode becomes like this, and the second mode becomes like this. So they look quite similar in terms of field distribution. They are quite similar in terms of resonance frequency. You see 4.16 and 4.70 gigahertz. And so you can use these 2 modes as to define the pass band of your filter. And this is what we have done in this case. So by controlling the insets, we control the resonance frequency of these 2 modes, and then we use these modes to define the pass band of the filter. So by a modal analysis of the cavity, we can make a preliminary design of the filter. After that, we make some fine-tuning of the insets, and we can optimize the response of the filter. If we use a strip line to feed this cavity, we can also suppress some higher order modes that are obtain a quite broad out-of-band rejection. And in this case, we have a 2-pole filter with the size of half wavelength times quarter wavelength. So we gain a factor 2 because we use a folded structure, and we gain another factor 2 because we use a dual mode cavity. This cavity resonates on 2 modes. So we reduce by a factor 4 the size of the filter compared to a traditional solution by using SIW cavities. Another way to reduce the size of the cavities is the half-mode solution, half-mode cavities. So same as in the case of half-mode SIW waveguide, we can exploit the presence of the magnetic wall along the symmetry plane of this cavity. If we remove half of the structure, we still keep a virtual magnetic wall due to the high capacitance along the open boundary, and we can reduce by a factor 2 the size of the cavity. Of course, in the case of the cavity, there is some degradation of the quality factor. We lose probably 30 to 40% of the quality factor. There are some tricks to do better, but more or less, this is what you need to expect. So a reduction of the quality factor around 30% compared to the completely shielded structure. And this is due to the radiation leakage through the open boundary. Of course, also in this case, you can simply combine half-mode cavities to obtain filters, or you can do something as we did for the folded structure. So we can insert some insets that control the first and second cavity mode. Can you hear me? I saw a message in the...
So now it's okay, sir. Sometime before it was not audible, now it's okay.
It's working okay?
Yeah, okay, sir. Now it's
okay, perfect, thank you. So in this case, again, we use 3 insets to control the first and second resonant mode of this cavity, and we can control the frequency response of the filter. In particular, we can control the bandwidth of the filter, and by avoiding the excitation of error modes, we can get a quite broad out-of-band rejection. In this case, the structure is excited by a microstrip line, and we have a single layer topology. So same advantages as in the previous case, more or less the same size, but with a single layer topology. There is a different way to look at this filter. In particular, we can say that we have the resonance of this stub and this stub, like in a modified microstrip filter. So if we consider these two stubs as resonating and responsible for these modes, we also have a easy interpretation of this other solution, where we have modified this stub. Sorry, I lost the pointer. This stub and this stub, and we have 4 resonance stubs that give 4 poles in the frequency response of the filter. So in this case, by using more or less the same size, we have a 4-pole filter in a very compact size, in the size that is approximately half wavelength times quarter wavelength. So in this case, we further reduce the size of the filter. The concept of the half-mode SIW cavity can be further extended if we consider, of course, one symmetry plane and we remove half of the structure, the other symmetry plane, and we remove another half of the structure. So in this case, we remove 3/4 of the structure and we get the so-called quarter mode SIW cavity. So instead of the entire structure, we get only 1/4. And this means that we have the fundamental mode operating at the same frequency, but with a time 4 reduction in the size. And we also eliminate some of the higher order modes that could create some spurious response in the filter. So by combining these quarter mode cavities, we can design a number of filters. For instance, we can combine 2 cavities. You see quarter mode cavity 1 and cavity 2, and we couple them by removing the row of metal cylinders in the common wall. And in this way, we can control the coupling by laterally shifting the 2 cavities or by increasing the distance between the 2 cavities. We can extend the number of cavities to 4, like in this case. When we remove the metal cylinders in the common walls, we get a filter with 4 poles. In addition, as you see here, there is a transmission 0. That is due to the coupling through this small metal strip from cavity 1 to cavity 3 and from cavity 2 to cavity 4. So by controlling the width of this metal strip, we can have a double transmission 0 very close to the pass band. And this, of course, helps increasing the selectivity of the filter. There is another possibility to exploit quarter mode filters, like in this case, where we have the filter coupled at their corners, and on top of the 2 quarter mode structures, we have a coplanar half wavelength resonator. So in this case, we have cavity 1 that is a quarter mode cavity, cavity 2 that is the coplanar half wavelength resonator, and cavity 3 that is another quarter mode structure. So the topology of the filter is shown here. We have the input port connected to cavity 1, that is the first quarter mode, that is connected to the coplanar resonator and then to the second quarter mode or directly from the first to second quarter mode. With this topology, we get a filter with 3 poles and 1 transmission zero. And you see that the size, also in this case, is extremely compact. It's less than half a wavelength, and we have 3 poles and 1 transmission zero. So we have different solutions to miniaturize the structure, and we can, of course, obtain different filters, different structures in this way. What we can also do is trying to fully exploit the flexibility of SIW technology, for instance, by playing with the material of the substrate. This is an example. This is a ridge SIW where we adopted the traditional topology, so the waveguide, so the SIW with the metal cylinders here and here, the partial high ridge post here, but we adopted 2 different materials, one for the bottom dielectric layer and the other for the top dielectric layer. In particular, we use high permittivity for the bottom dielectric layer and low permittivity for the top layer, which is the reason. The fundamental mode, looking like a T10 mode, is mainly concentrated in the bottom substrate. So it is subject to high permittivity, so its cutoff frequency goes down in frequency. It goes down because of the presence of the ridge. It goes further down because we use a high permittivity material. The second mode is also distributed significantly in the low permittivity material, in the top dielectric layer. And so it's subject to a lower dielectric permittivity, and it is shifted up in frequency. By adopting this solution, we could obtain a ridge SIW with a single mode bandwidth ranging from 2.5 to 12 gigahertz. That is quite large bandwidth, and that covers completely the UWB band, including the 2 margin bands below and above the nominal bandwidth, nominal ultra wideband standard bandwidth. So in this case, we use 2 different materials. If you want to use one single material, what you can do is removing a portion of the dielectric inside a cavity. In this case, for instance, if you have a rectangular cavity filled with a homogeneous material, this is the fundamental mode TM110, and this is the second mode TM210. Okay? If you remove a portion of the dielectric inside the cavity, in the central part here, what happens is that you get 2 modes that look like this, because the electric field tends to concentrate in the area with the dielectric, simply because they have somehow a lower impedance. So the electric field is more concentrated here and here, so in this part and this part. And these 2 modes that are originally this and this that you see in the homogeneous cavity become quite similar, with the only difference is that one has even symmetry and the other has odd symmetry. And also, they can go quite close in frequency. In particular, if you consider this kind of structure to design a filter, so the cavity with the air field structure cover top and bottom with metal layers and fed by microstrip lines, you can see that if you change the length of the air field area, what you can do is controlling the frequency separation between the first and second mode, that is approximately 20% in the case of a homogeneous cavity, it can go down to 1 or 2%. So this means that if you want to use these 2 modes to design a filter, so these 2 modes as to define the pass band of your filter, you can select this dimension to obtain the resonance frequency of these two modes with the desired frequency separation. So from the modal analysis, you can design your filter. You can select the bandwidth of your filter. Here there are a couple of examples. In the top part of the slide, you see a narrowband filter. You see here with two transmission zeros that are due to the unbalanced excitation of the two cavity modes in one case, and to direct input-output coupling in the other case. And you also see in the bottom part of the slide a broadband filter. Basically, if you increase the length of the air filter region, you reduce the bandwidth of the filter. If this length is small, you have a broadband filter. If this length is large, you have a narrowband filter. This can be seen, can be physically explained if you consider this as a resonator, this is another resonator, and this as a waveguide below cutoff that couples the two resonators. If the waveguide below cutoff is longer, you decouple the two resonators and you have a narrow band. If the waveguide below cutoff is short, you couple more the two resonators and the bandwidth is larger. Of course, you can also design more complex filters like fifth order filter. Like in this case, you have a dual mode cavity here with the air field region, a traditional single mode cavity in the middle, and another dual mode cavity here. So you get a filter with 5 poles and a double transmission zero here. The other transmission zero is quite far away and cannot be controlled. We can do the same by using a complementary solution. So we can remove the electric in the side portions of the waveguide, of the cavity. In this case, we have air field regions here and here. And the resonant modes in this case look like this. What we do is using the second and third mode to design the filter, and the fundamental mode here as a non-resonating mode to introduce a transmission zero. In this case, the structure is excited not by microstrip line, but by coaxial probes. You see here and here. This filter is quite interesting because depending on the position of the coaxial probes and the aspect ratio of the rectangular cavity, you can obtain transmission zeros, two transmission zeros that are both below the pass band, both above the pass band, or one below and one above. And basically, it depends on the dimension of the electric field region in the center. So if you have the two coaxial probe aligned with the long side of the cavity, depending on the sequence, which mode has lower cutoff frequency, either the 120 or the 210, you can have one transmission zero below the pass band and one above, or both below. If you have the coaxial probes aligned with the short wall of the cavity, you can have the transmission zeros both above or one below and one above. So you have all possible combinations of transmission zeros in this case. And you see here the implementation of a couple of these structures. One with two transmission zeros above the pass band, and the other with one below and one above. So also in this case, of course, when we fabricate the structure, we remove everything, the electric and metal, and then we use copper layers to close the cavity at the top and the bottom. You see here the sandwich structure that we implement at the end. And you see here the holes to mount the coaxial probes, and also at the top there are the holes that allow to solder the central conductor of the coaxial probe with the top wall of this layer. Another structure that we implemented a few years ago was a Wilkinson type power divider. In this case, what we did was having a E-plane power divider, and we inserted between the two layers a resistive card that implements the resistance that is typically adopted in the microstrip line, or let's say in the traditional Wilkinson dividers. And you see here that we have a quite balanced power divider, a division, and a quite good phase difference below 5 degrees over the entire band of interest. So the other topic that I would like to discuss with you in this presentation is related to the use of unconventional materials. So for decades, microwave engineers have been used to adopt either metal, conductors for waveguides and so on, or the electric material like PTFE or similar materials or alumina for microstrip line structures. With the current applications in the area of IoT, there is a need to broaden a bit our field of view in terms of materials. And we also need to consider some materials that have never been used for micro applications. And I talk in particular about textile and paper. Textile is good for wearable devices. Paper is good because it's low cost and eco-friendly. There is another material that is becoming very popular in the last years, and is the 3D printing material. And the main reason is that in this way, we can obtain fully 3D structures. We can play with the density of the material. We can obtain unconventional shapes, and really we can add degrees of freedom in the design of our structures. So I will start with 3D printing, and then we will go through the other materials. So as I said, 3D printing is becoming very popular for different applications, from medical applications to building construction to many different areas. And nowadays the cost of the 3D printers is reasonable, and let's say can range from a few $100s to let's say thousands of dollars or even more, especially if you consider metal printers. Printing of metals. What I will present to you is a 3D printed plastic material. So we use the printing material. It is the most cost-effective solution. And in this slide, you see the first SAW structure that we implemented by using 3D printing in conjunction with a group of Rosamano Stenseris at Georgia Tech. That was in 2015. And you see that you can also play with the shape. You can have like 4 bands in the E-plane, this kind of bridge. This is something that you cannot do by using standard PCB technology. It's very hard to obtain a shape like this. So you really have complete flexibility. And the advantage is that in this case, you can simply design your structure by using a EM solver, pass the file to the printer, and in very short time, you have your prototype. So for fast prototyping, that's a fantastic solution. Also for investigating unconventional shapes or new solutions. Of course, this structure is not very useful. It was just a demonstration of the possibility to have SAW structures by 3D printing. This one is definitely more interesting because it is a microfluidic sensor. So the idea is that we 3D printed a SIW cavity with a micropipe inside. So we directly printed the pipe inside the cavity. And the idea is that when we inject a liquid in the pipe, for instance, by using a syringe, this liquid inside the pipe can change the effective permittivity and effective loss tangent of the material inside the cavity. The net effect is that we observe a variation of the resonance frequency and of the quality factor of the cavity. The shift of the resonance frequency and the variation of the quality factor can be used to retrieve the characteristics of the liquid. So this structure was originally presented in 2015, was done in conjunction again with Professor Maurizio series, and then we had to work a lot on the extraction technique, and we published recently a paper a couple of months ago. Got a strange message. Can you hear me?
Yes, sir, now it's okay.
Okay, because I got a message.
Yeah, a few seconds before it was not audible for a few seconds. Now it is okay.
Okay. Okay. So I try to go back to the presentation mode. Okay. So in this case, when we inject a liquid in the cavity, we change the resonance frequency and the quality factor. And so from the measure of the variation of resonance frequency and quality factor, we can retrieve the characteristics of the liquid. So this is quite interesting because we implement, by using 3D printing, the so-called lab-on-chip, a very simple and cost-effective structure that can be used for medical applications or for a variety of different uses. Another structure that we implemented by using 3D printing was a slab SIW. As I told you, in the slab SIW, you can drill some holes in the side portions of the dielectric material to lower the permittivity for the second mode of the waveguide and increase the operation bandwidth. Well, in this case, we implemented the slab SIW by using 3D printing, so there was no need to drill the holes. In one fabrication pass, we got directly the prototype that you see in the right-hand side of the slide. You see the side portion has a lower permittivity than the central portion. So if we have a standard SIW structure, we have the bandwidth ranging from 3 to 6 gigahertz. If we have a slab SIW, the single mode bandwidth is from 3 to 7.5 gigahertz. So we gain 50% in terms of bandwidth simply by playing with the density of the material in the side portions of the SIW. If we consider textile material, we can do a lot of interesting structures. This is an activity we developed a few years ago in conjunction with the Ghent University in Belgium. And the reason to develop this structure was the need for localization systems for firefighters. So when a firefighter enters inside a building, there is no way to localize the person by using GPS. So it was needed to develop a localization system that could be easily integrated in the jacket of the firefighter. And one of the critical aspects for these localization systems was the antenna, because when they try to use patch antennas, the mounting of the patch antenna on body created a significant degradation of the performance. So what we did was using an SIW cavity-backed antenna. How do you implement a SIW structure on textile? Well, the idea is, in this case, was using as a substrate the infill of the jacket of the firefighter. It was a kind of rubber, a closed-cell expanded rubber with a thickness of 4 millimeters. And then for the top and bottom metal layers, we used an electrotextile called Flectron. And for the metal vias, we use rivets that are typically used for clothes or for shoes. And so it was quite easy to use them on textile. And then we implemented different structures, straight interconnects, filters, cavities, and so on. And in particular, we implemented this slot antenna embedded inside an SIW cavity. The big advantage of this structure is that when you have a microstrip line exciting the cavity, actually what happens is that the microstrip line excites the cavity and the cavity excites the slot on the opposite side. If you don't consider the cavity, what happens is that a portion of the power is starts propagating along the substrate. And of course, this reduces the power that is radiated by the antenna and also makes the antenna more sensitive to what's around the antenna, so the presence of the body. So when you measure a patch antenna or a simple slot antenna in ideal condition, they work perfectly. When you mount them on clothes, the movement of the arms or the movement of the body creates a shift of the operation frequency. If you do that with a SIW cavity around, so-called cavity-backed SIW antenna, you somehow shield completely the antenna from the environment. So the presence of the body does not affect anymore the antenna. And this represents a very good solution for wearable antennas. So this received also an award in electronic letters a few years ago. Another material that we adopted for implementing SIW structures was paper. And the main motivation was that paper is extremely low cost. So for some applications like, let's say, RFID-like structures or low-cost sensors, it could be a very interesting solution. And the other reason is that it is eco-friendly. So for some areas, some fields of applications like agriculture, for instance, if you want to have some sensors that to be adopted for agricultural purposes, using eco-friendly materials could be preferable because you don't pollute the field where you want to perform some measurements. So this work was partially performed in conjunction with Georgia Tech in Atlanta, Professor Manos Tenseris, and we adopted two possible solutions. So one was using inkjet printing. So we use a special printer that prints ink with silver particles to give the proper shape to the conductive parts. So you print your conductors, then you put in the oven at low temperature for something like half an hour or 1 hour. The ink evaporates, the silver particle melts, and they form a conductive film. So this was a quite interesting solution that allowed to implement straight interconnects, cavity filters, or slotted waveguide antennas, like in this case. But there was also another solution that we implemented in Pavia that was based on the use of aluminum foils. So in this case, we adopted a thick paper layer, and we glued on both sides aluminum foils. This solution permits to obtain a laminated substrate like the one you can buy from a retailer like Taconic or Rogers or these providers. Okay. In this case, we adopted an epoxy glue to paste the aluminum foil so that the surface becomes very hard, and we can use a micro milling machine, LPKF machine, to remove the excess metal, exactly as we do for any laminated that we buy from commercially. So in this case, you can imagine that the accuracy is very good because it's a very well-defined fabrication process. And you can see here an example. This is a filter like the one you have seen before. This is a half mode SIW, and this is a quarter mode cavity filter. So this is another possible solution to implement SIW circuits on paper. I think this is the conclusion of my presentation. What I want to remark is that SIW technology is a very powerful technology for implementing a variety of components at microwave and millimeter waves. But especially, it is one of the best candidates when you want to realize complete systems, because it permits to implement all parts of your circuit by using the same fabrication technology and permits to interconnect the different parts in a very simple way. What I have shown you is just a partial view of what can be done. There are a lot of other areas that have been explored and still deserve some research, like multi-layer integration or reconfiguration of the structures, the use of materials like silicon or CMOS processes to integrate SIW structure. There are some groups in the work doing very well in these areas with operation frequencies up to more than 100 gigahertz. And of course, selection of materials. So there are different applications that can require different level of accuracy, different level of performance, but they all can take advantage from the use of SIW technology. I think this concludes my presentation. I wish to thank you very much for listening, and I'm available for questions.
Sir, thank you very much, sir. So thank you very much, sir. Actually, there are some questions from the audience. I can probably read out. Maybe you can interact with them, sir.
Okay.
The first question is from Shashmita Das. Can SIW technique work at terahertz frequency?
I cannot hear you very well.
Oh, sir, I'm audible now?
Yeah, now it's much better, yes.
So the first question is from Ms. Shashmita Das. Can SIW technique work at terahertz frequency?
That's a good question. So far, there are some examples up to few hundred gigahertz. If you go up in frequency, if you go beyond 300-400 gigahertz, of course, the loss in the materials and the loss in the conductor becomes significant. So probably if you go to the terahertz region, there are other solutions like NRD structures that could be more interesting. They are not yet fully developed. There are some work, actually there was some work some 10-15 years ago, but somehow it stopped. But I still believe that NRD is probably better when you go to the terahertz regime.
So thank you, sir. We'll move on to next question. A question from Ms. Tenmari. Mostly SIW structures are used for about 10 gigahertz. Is there any specific reason behind this?
So there are two reasons, I would say. One is that the size increases when you go down in frequency. We have seen that there are multiple solutions to reduce the size. So in principle, you can go down to maybe 1 gigahertz or below 1 gigahertz with SIW and still have a quite compact structure. But at this point, the question is, why don't we use a microstrip line at low frequency? Because when we work at 1 gigahertz, the microstrip line is perfectly fine. losses are reasonably small, you can get quite good confinement of the field with a limited spurious radiation. So below 10 gigahertz, it's possible to use SIW, it's possible to miniaturize SIW structures, but it is less competitive when we compare it with the microstrip line. Of course, it depends on the applications. If you want to have a completely shielded structure, maybe a system where you stack different layers and so on, it can be interesting to use SIW. But for many applications, at few gigahertz, microstrip lines work pretty fine.
Yeah, thank you, sir.
Dr. Karthikeyan, this is Dr. Karthikeyan. This is Chinmoy Shah from IIST Trivandrum.
Yeah, welcome, sir.
Can I have some comments to Professor Bozzi and some technical questions as well?
Yeah, definitely, sir. Definitely, sir. Please.
Yeah. So firstly, on behalf of MTTS Kerala chapter, I congratulate Professor Bozzi for this wonderful talk. This is one of the best talks I have ever attended in the area of SIW technologies. So for the audience interest, I would just want to inform that Professor Bozzi has very strong India connection. He has co-authored a book with Professor Ramesh Garg, and he has given us enormous opportunity through IMARC in different versions and visits India quite frequently. So we have been really benefited with his association. So thank you very much, Professor Bozzi. And
thank you very much for your nice words. It's always a pleasure coming to India for me. Really.
Yeah, and on behalf of MTTS India also, I would convey my best thanks to all of you, because the MTTS ATCOM is so generous to us. I mean, we are having IMARC, the special events in India every year, and moreover, this MTTS chapter of NIT Trichy started another initiative last year in the form of IMICPW 2019. So where these students and Professor Karthikeyan are involved, I was also involved in the process. So thank you very much for the support from the society. Yeah, so
thank you very much. It's a pleasure.
Yeah, I have a generic question to you on behalf of all the students here in India in different parts. Actually, one of the limitations is the fabrication technology, fabrication limitations in SIW, especially when we move to 5G, 28 gigahertz and 38 gigahertz. So can you please highlight what are the fabrication facilities and the cost involved as far as Indian scenario is concerned? Yeah, this is the first part of the question. And another part I'll come to later on.
Okay. There is an interesting point about fabrication. I don't have the slide here, but we made some tests a few years ago, and we designed exactly the same filter with the same frequency response by using microstrip line technology with a couple of resonators, and by using SIW with inline cavities. And then we try to play with the simulator to investigate the sensitivity of the two structures. And we try to have a 50 microns inaccuracy, either in the position of the couple resonators, and both in the position of the couple resonators and in the position of the metal vias of the cavities. And what happened is that with 50 microns accuracy, the filter in SIW technology practically didn't change much, a little bit the input matching, whereas the filter in microstrip line was completely destroyed. So SIW technology is more robust than microstrip line technology in terms of fabrication inaccuracy. And for this reason, it could be interesting to invest in the fabrication of this structure rather than microstrip line, because you can go with a given accuracy to higher frequency. Concerning 5G, well, in my lab we have a very simple tool. We have a LPKF machine for fabrication of SIW structures. and the cost was approximately $10,000, more or less. And this allows to fabricate easily SAW structures up to 20 gigahertz. If you want to go to 29 or 38 gigahertz, probably you need something better. Probably the cost can be twice or three times higher. This is probably what you need for that kind of fabrication.
Yeah.
This is more or less. And for the metallization, there are different solutions, but they are all quite cost effective. So the major cost is a milling machine for making the holes and removing the metal. And this is more or less the cost that you expect.
Okay. Thank you very much. The second part of the query is you mentioned regarding the connection between SIW and IoT's Internet of Things. So can you just elaborate the applications of SIW on different IoT scenarios from IoT perspective?
So recently, we have been working on let's say, a follow-up of that microfluidic sensor that I've shown in the slides. And in that case, we have a resonant cavity that changes frequency depending on the liquid you put inside. So what we did, the following step was adding a transistor that uses that cavity as a frequency selective element. So we get an oscillator that changes its resonance oscillation frequency depending on the liquid. The next step will be using the signal coming out from the oscillator to feed an antenna. So in that case, you have a sensor. On top of the sensor, you mount a transistor, you attach the output to an antenna, and you have a wireless system. Of course, this is a very simplified version of the story, but this is something you can do very easily to develop wireless sensors.
Yeah, I understand. Yeah, thank you very much.
Thank you very much, sir.
You're welcome.
In line with so Dr. Saha question, actually I also have one doubt. You have shown some of the 3D printed structures. Actually, sir, am I audible, sir? Bozzi, sir?
Yes, sure. I hear you.
So you have shown some 3D printed SIW structures, sir. Anyway, that 3D printed substrate we can make using maybe either FDM with the help of ABS or maybe PLA, some other material. How to deposit the copper over that, sir, actually?
Yeah, this is still one of the big question marks for 3D printing. What we did currently is using we use a spray, a conductive spray on the surface of the 3D printed structure, and then we use electroplating.
Okay, sir. So conducting spray means with the help of mechanical pump or through inkjet printing machine, sir?
No. I mean, in most cases, we have to metallize everything, so we just use the spray manually. Okay. What you can do is print some electric, I mean, by using a 3D printer, you can also print something that you peel off at the end after metallization. So this is the other possibility. The next step, what we are trying to do now is using printing directly a surface layer of a material with some conducting particles. It can be either graphene or some conductor, let's say, melted in the filament. And in this way, the surface is already conductive, and we can put it directly in the electroplating machine. But we are still at the very beginning for this. So this could be a step forward. So we print the entire structure by using the electric material. Then we print a surface layer that is partially conductive, and we can use that directly with electroplating for the metallization.
Okay, sir.
This is something we are trying to do in these weeks.
Okay, sir. Okay, sir. Thank you, sir. Sir, almost we are so nearing up the closing time. So many questions are from participant. I just request participants to mail to the speaker. So individually, maybe if you have any questions. Sir, let's have some feedback from some professor. I invite Dr. Saha to give his feedback on this webinar. Chinmay sir, are you online?
Yeah,
Yeah, sure.
thank you very much. I already interrupted. You know, the best talk I have ever attended. Especially, I mean, in spite of this webinar mode, the way he explained the stuff, starting from the very basics and giving the full horizon of what are the applications. So I think that should give a lot of impetus to the youngsters, the young researchers, many of whom I personally know who are attending this event. So, you know, it's a very well planned, well thought talk. And nothing more to say about Professor Bozzi. He doesn't need any introduction. He's like one of the probably like Mount Everest in the field of microwave circuits. Yeah. Yeah, as your Google citation also suggests, you are in terms of meter and your is in terms of number. Probably like that. I thought of giving this analogy. And yeah, it was indeed a very good job, and we would be really loving to see you sometime, probably difficult this year, probably next year. I know you'll, because of your strong association with India and strong link through IMARC, you'll be coming. So at that time, please visit us, visit NIT Trichy and to my institute, because we are not far. These two institutes are just 400, 500 kilometers, which is like 1 hour in air or maybe few 3 to 4 hours in train. So thank you very much and stay safe. Yeah, that's it from
Thank you
my
very
side.
much, and it was a real pleasure for me to give this talk for your studio branch chapter, and I was really delighted of your invitation. Thank you again. Thank you very much.
Yeah, thank you.
Thank you, Dr. Chinmay. So thank you, Dr. Chinmay. Now I request Dr. Devdeep Sarkar from IIC Bangalore to share a few words with us.
Yeah, am I audible?
Yeah, yes, sir.
Yeah. Okay, so well, I will not repeat the exact thing what Dr. Shah said. I think it was a very enlightening talk from Professor Bozzi, and I think this is the first time I have heard to him. I have I learned about him from some of my colleagues who are working on the same area, and this was like very much enlightening talk for me. I could understand the basics, like how to start, and I think similar to me, many other young professionals or people who are just starting their research career, they would be immensely benefited from the way he explained for starting from the basics, and he went to the advanced applications and all the things. Thank you, Professor Bozzi, once again for like speaking on this topic. And I also like to thank Dr. Karthikeyan and Noshinga, who have worked extremely hard to prepare this webinar and just to bring it out for the sake of the community. So I'll thank everyone, and just one small question to Professor Bozzi, that what do you think that would be like the most promising research direction in this SIW technology, like in one line or two line, if you have to say. So if you just mention that, that would be very nice. Thank you.
I think there are two areas nowadays. One is, let's say, easier to implement in a short time. The other is more futuristic. The one that is important today and easy to implement is reconfigurable circuits. So we can use reconfigurable cavities, but also reconfigurable transmission lines.
Okay.
And the long-term perspective, in my view, I mean, already discussed many times also with Professor Kewu, who is somehow the father of SIW about this. But the real step forward would be distributed amplification. So it could be nice to do with SIW what is done with fiber amplifiers in optical fiber. So to have some kind of pumping of energy from the sides and having distributed amplification during the propagation of the wave. So this would be really the big step forward for SIW technology, but it's a problem of materials. So it's important to connect with material scientists, with people from Department of Chemistry, with the physicists, to understand if there are some materials that allow this effect at microwave frequencies. This could be really a big step forward. So reconfigurable devices in the short term and distributed amplification in the long term. This is probably the important areas in my view.
Sir, thank you very much, sir. So now we are come to the end of the session. So it's my formal vote of thank you. Am I audible now?
Yeah, thank you so much for organizing this event.
Thank you very much, sir. Actually, you readily accepted our invitation from MPT chat of NIT Trichy. So amid COVID pandemic. So thank you very much for your acceptance, and also your lecture is very much useful. So because most of the people are working in SAW in India, and as Dr. Saga said, so really you have started from the basic and you have shown more innovative and advanced way of designing various SAW circuits. So definitely it will be very much useful for the young researchers, those who are working in this field. So thank you very much for your informative and useful lectures. And also I thank all the participants, many number of participants registered. Actually the attendees are so nearly 200. Exactly it is comes around 195 attendees. They effectively and attended the session for the whole duration. So thank you for the participation. And also personally I thank Dr. Saha and Dr. Bozzi Sarkar for joining us and to share their views. I thank my MTTT student chapter chairman Narsingh Birdhan and our IEEE student branch counselor Dr. MP Selvam and secretary Mr. Kannadasan. So thank you very much everyone. So hope we can meet you sometime in India during IMARC's time, sir. So thank you very much.
It's really a pleasure. Thank you very much.
Thank you very much, sir. Thank you all.